to talk about depth-first search. It will be like in our video algorithms design 12, but with a twist. Depth-first search usually doesn't deal with graphs where there are multiple source options, but this has a twist where we just pick one vertex that can get anywhere and go with it. We will also be adding in a counter while making a tree to the right. We will add a preorder number and postorder number to each vertex as we go. We will first travel to C because C has not been discovered yet. This will be a normal tree edge. We will choose arbitrarily between our options from here and go to F. F can't go anywhere, so we will consider it finished, which will fill in its postorder number with our counter. Because F has a postorder number, we will backtrack one. C has one more option, which is to go to D. Then we'll travel to B. B only has one option, and that is to travel to A. However, A has already been discovered. Because B is a direct descendant of A, this connection will be a backedge. Backedges are an important thing to take note of. They will exist if and only if there is a cycle. Directed acyclic graphs, DAG, will never have these. We will backtrack to D and travel to E, and then to H, and then to G. The only place for G to travel is to F. F is a vertex we are finished with, and is not a direct descendant, so this will be a cross edge. Once again, we will backtrack until there is another connection we have not explored. D discovers F, which is another cross edge, but when D finds H, we can see that H is finished and is a direct descendant. This is called a forward edge. A fun thing we can visualize is to rearrange the vertices on the tree. If when given an arbitrary choice, you were to make the other, these two would still be topologically equivalent. The colors would just be different. Like I said before, directed acyclic graphs, DAG, don't have any back edges. It seems like a redundant name because undirected graphs are automatically cyclic, because you could just bounce back and forth. But they never asked for my advice on naming things, since I tried to name a bunch of algorithms after my cats. This is what's called a topological ordering. We can rearrange this too. Two vertices are called strongly connected if each can get to the other. For example, A and H would be considered strongly connected because H can get to A by going through H to I to B to A, and A can get to H by going through A to G to H. In fact, all 5 of these vertices are all strongly connected to every other one. Let's just put all of them in one big bubble. These larger bubbles are called strongly connected components, or an SCC. We will put the vertices outside of a large one in their own SCC, even though they're probably lonely in there. We could treat each SCC as sort of a node itself. The topological ordering of these will always be a DAG. This is because if there were to be any way back once you went somewhere, those two SCCs would be strongly connected and become one SCC. There's often more than one order that the topological order can go in. To find an order, we start with a source, which in this case must be A. We then delete A in the graph and every arrow coming from it. We then look at our new graph and find its source and repeat the process. If you ever have more than one choice, you choose arbitrarily. To fill in the arrows, we simply go back to the original graph and one by one connect them topologically. If we wanted to find all topological orderings, we go through the same process until we get to a choice and then split. Let's make a reachable tree, looking at what we can see from all the vertices currently discovered, assuming all sources are visible from the beginning. I don't actually know the name of this type of tree, so for now we can just call it a reachable tree. Because there are two options now, we will just look at the B path and come back later to look at C. We will explore each possibility until the reachable tree reaches the height of the number of nodes, and then track back to the last place we left one hanging. If we track the topological order through our reachable tree, we can see that there are two yellows on the bottom row. This tells us that there are two possible topological orderings. All the topological ordering options will always be a subset of the reachable tree. The most options you can ever have will be n factorial, where n is the number of vertices. Now, for depth first search with the preorder and postorder. Like with the topological sorting, all possibilities for the DFS will be a subset of a reachable tree. The vertex with a 1 as its preorder number and 2 times number of vertices reachable by DFS is a source. All the options of our source for a DFS will be in the top row of our reachable tree. The most options you can have will be n minus 1 factorial, where n is the number of vertices. If you search for any vertex where its postorder is only one bigger than its preorder and all vertices are reachable by a source, you will find all the sinks. The bottom row of the reachable tree correlates in this case, but won't tell you anything for sure. Let's overlap the topological ordering and DFS order on their reachable trees and color any space where they overlap orange. In the overlapping graph, you can see that it can contain all 4 possible colors. I like that symmetry in the graph makes symmetry in the rest. It's pretty. When there are multiple sources, the DFS options will never reach to the bottom row. This is because there is no way to a source unless you start there, and you can only start in one place. In the DFS preorder and postorder trees, you can sometimes see and find all the sinks, but not always. All sources will be orange in the overlapping tree, but can go on for different lengths of chains. This includes a possibility where only the source node is orange. As you can see, these trees get pretty chaotic pretty fast. Wait, why didn't I name the reachable tree Mr. Whiskers?
What?
I'm sorry, my kitty.